This is Jack Jackson. We're going to look at adding vectors today. So last video we talked about defining vectors. We saw that we could see them in both component form and in magnitude and direction form. Today we're going to talk about adding vectors. So geometrically it's pretty easy to add vectors. We just draw the first vector, and so we think of this as a displacement. We're going to think of this vector u, and we're going to think of starting with our point here at the tip, or the tail of u, and ending up at the tip here, so it just moves along like this. In this case we're moving 3 to the left and 4 up. You can change that vector by typing in those numbers in this sketch. You can place this vector anywhere you want, remember, and it's the same vector, so it doesn't matter where we place it. However, when we add vectors, we want to place the initial point of the second vector at the terminal point of the first vector. So you want to think of adding vectors really as the composition of translations. So we start here, we apply the first vector, which says we go left 3 and up 4, so that gets us to here. And then from there we go left 1 and up 3, which gets us to here. And so the net result is we're going from this end to this end, and that is the vector sum right there. So that's what we get by adding them together. Okay, so what is another way we could have gotten to the same place? Another way we can think of this is if we think about the components. So here you can see the components, and you see the components of the resulting vector u plus v. So the red one is, let's just get our letters straight here. So u is the original blue vector, the first vector. Then v is the green one, that's the second one. And the sum is the red vector, u plus v. So we see that to get this resulting vector, what about its components? Well, look at how much we displace on the blue one, which would be from here to here. Okay, and then from there we displace the green one, and we're just adding those two things together. And the vertical displacement on the red one is adding together the blue displacement and the green displacement. So we see that it's pretty easy to add these things together in component form. So this leads us to an algebraic definition. It's our formal definition of vector addition. To add two vectors, we just add the x components to get the x component of the sum, and we add the y components of our two original vectors to get the y component of the sum. So in our example, we've got negative 3, 4, and then we're going to add to that negative 1, 3. So to get the resulting vector, we add the negative 3 and the negative 1 to get negative 4, and we add the 4 and the 3 to get 7. So this says if we go to the left 3 and then up 4, and then from there go left 1 and up 3, we might as well have just started at the beginning and go left 4 and up 7, which is the result, which would get us to the same place. So that is the component form of the vector u plus v. Okay, now this generalizes nicely to higher dimensions. So we'll often want to use vectors in 3 dimensions. They'll have not only an x and y component, but then a z component as well. And so this will be vectors in space. But actually you can even generalize this to vectors with any number of dimensions. So you can talk about n-dimensional vectors. They're a little harder to visualize once we get past 3 dimensions, but nevertheless we could define them. And so if we're adding two vectors of the same dimension, it's pretty easy to add them. So we could say the components of vector u could be u1, u2, u3 up to un, and then the components of vector v would be v1 plus v1 comma v2 comma v3 up to vn. And when we add them together, we just get u1 plus v1 for the first component, u2 plus v2 for the second component, u3 plus v3 for the third component, and so forth up to the last component, which is just un plus vn. And so we can add any vectors, any two vectors, as long as they have the same dimension. Most of our work will be in two-dimensional vectors, maybe some three, but this does generalize to higher dimensional vectors. So if you have two vectors given in component form, it turns out it's quite easy to add them together. Okay? So how do we add them together if we're given magnitude and direction? Well, as far as geometrically goes, it's not too bad. This one, let's see, let's put some easier numbers in here. Let's just say 5, and let's go at a direction of negative 50 degrees, or positive 50, that'll work. And then let's go 7, and a direction of how about negative 30 degrees. Okay, so again, start here at some point. Our initial point in this one's going to be B. We're going to go from B to C to A. Okay, so B here to C here, and we're going to end up at point A here. This vector is the vector A plus B. This is vector A is blue, vector B is green, and the resulting sum is vector A plus B, which is in red there. Okay, so again, geometrically it's not hard to do it. You find your horizontal here, pick a point, go horizontal from there, measure up an angle of whatever it is, 50 degrees in this case, and then go out along that ray, however long it says, 5 centimeters. You could do this with once you had a horizontal established, then you could measure an angle with your protractor, go out a certain distance with your ruler. Then you've got point C, you've got vector A. Put the arrow on the correct end, you've got it. Then from there, where it ends at point C, again draw another horizontal, and then measure an angle of negative 30 degrees, and go out a length of 7. Again, you could do that with a protractor and a ruler. And then the resulting vector is this vector, red vector here. Now, as far as doing the computations here, how do we get all these numbers that you see here? Well, one way we could do this is through, well, there's actually two options. One option is this. Now, remember, it's very easy to add these things together if they turn out to be in component form. So let's put them in component form and then add them together. So here's option 1. Resolve these into components. So remember the component form, x is r cosine theta, y is r sine theta, where r is the magnitude. So for A, that's 5 times the cosine of 50 degrees, comma, 5 times the sine of 50 degrees, which works out to be approximately 3.21, whatever, comma, 3.83. That's how much you go to the right and up. Similarly, B is r cosine theta times r sine theta for the r and theta for angle B, and so that's going to be 7 cosine of negative 30 degrees, comma, 7 times the sine of negative 30 degrees. So in this case, that's about 6.06 to the right, and then we got negative 3.5, so that's down 3.5. So then, just to add them together, we're adding those two component forms. Now it's pretty easy. Add that component, add the x components, add the 3.21 and the 6.06 to get approximately 9.276, etc. And then similarly add the y components, and you get approximately 0.033. So this goes quite a bit to the right and just a little bit up. About 9.276 centimeters if that's our distance unit to the right, and 0.33022 centimeters up. And that's what you see here in the red. Then we can figure the so that's our sum, but if they give you the vectors in magnitude and direction, they probably want the answer back in magnitude and direction. So we have to now go back and compute the magnitude and direction of this vector. Magnitude's pretty straightforward, just use the Pythagorean theorem basically. So square each component and add them up. That's 86.15537 roughly in square centimeters. Square root of that is going to be the magnitude, or approximately 9.28199 centimeters. So about 9.28 centimeters. And remember, the tangent of the angle is y over x, so it's the 0.33 over the 9.276. And we have to kind of look at our picture to see what's happening here. So actually the inverse tangent of this is an acute angle, and in this one is an acute angle. If you think of the B as the origin, then this is in a first quadrant kind of an angle if it's in standard position. And so the angle is pretty small there, close to 0. It's 2.04 degrees. Now, depending on what these things are, let's do in what direction the angles are. We can get all kinds of different situations, and so you may experiment with these a little bit depending on how this thing works out. Also over here in this, I have some other angles here kind of measured and worked out here using Sketchpad, because you may have to do this in the context of a problem where you might, instead of measuring your angles as we do in math, you might want to measure them in terms of, say, heading or bearing or something like that. But the angle you put in here in the formula is the regular math way of measuring your angles. So that's one option. One option is to rewrite things in terms of components. Another option is to look at this picture that we have and notice that we have a triangle. Notice that we know side A and we know side B, and we know enough about the angles to be able to figure out the angle at C, where these two, where you're at the end of the first vector and the beginning of the second vector. Okay, so let's see if we can figure that out. So magnitude of the well, we can use the law of cosines now to find this. First of all, we need to find angle C. Okay, so you have to look at the context to see what angle C is. Actually, it should be probably the absolute value of that, 110 degrees. So let's take a look and see what we've got here. Well, we know the angle here on angle A is this angle right here. That's the same as the angle here by the Z property, or alternate interior angles of, can you see the Z here, letter Z? And the little corners of the Z are going to be the same. So if and only if these two lines are parallel. So since these are parallel, they're both horizontal, this angle here for angle A, the direction angle, which is 50 degrees, is the same as this little angle right here. Now the angle for B is 120 degrees. Well, that's a reference angle of 60. So 60 plus the 50 is 110. So this is 110 degrees. I've got it measuring it in the opposite. I've got this as a directional angle and have it the opposite way. I need to go ahead and just have that do an absolute value there, so it'll come out positive. But in any event, we're taking the cosine of it, which is an even function anyway, so it doesn't really matter. So anyway, you work this out using the law of cosines to find the measure of the other side. So the norm or magnitude of vector A plus B, in other words, side C of our triangle, is the square root of A squared plus B squared minus 2AB cosine C. That's the law of cosine solved for a side. So just plugging in the numbers, A is 5, B is 7, those are the magnitudes. Again, they come up here and here, and the angle there is the angle we figured out for C, which is 110, should be a positive 110. And then the magnitude turns out to be there, almost 10, 9.89654 centimeters. Now we can also use law of cosines to find the angles, and the angle we really need is this angle at B, the angle between the original blue one and the red one. Now that's not the angle we're going to need for the direction angle, but it'll help us figure out the direction angle. So we can use that interior angle, measure that find the measure of that interior angle with the law of cosines using b as the inverse cosine. A squared plus c squared minus b squared over 2ac. Remember to put the parentheses around the numerator and denominator here. So it's inverse cosine here. And in degrees, that turns out to be about 41.66 degrees. That's the angle between the red and the blue. But remember, in the way this picture is drawn, we also have to add the blue to it, which was another 51 degrees, so that gives us 91.66 degrees. It depends on the way the shape of this looks, whether you're going to be adding things together or subtracting them. So you need to experiment with this with several different cases. So I strongly encourage you to get in this sketch, try out some different ones, and make sure that that you can get these things to work out, and practice this. So two options. Option 2 that we're doing now is basically figure out the angle between the two original vectors here, the way they're put together, and using the original direction angles. And then also, you know the lengths of the sides, so you've got side angle side. Use law of cosines to find the other side and the angle. Use that angle of the interior angle. Use the at B is the interior angle you need. At the side, of course, side C, the magnitude you're looking for there. And then use that information to, particularly the angle at B and the direction angle for A, to somehow figure out what the angle is for the direction angle for the sum. That's one option. The other option, remember, was to resolve things into components and add those two components together and then turn it back into so basically go from x and y to r and theta. Go from r and theta to x and y, add them together to get an x and y, then go back to r and theta. So do it that way. So two different ways to go at it when you're given a magnitude and a direction. Briefly, I want to show you one more tab. This particular tab here is looking at the difference in two angles. Okay, so if you do, this is going to be, so notice the way this is done. Watch the arrows. If I follow the purple B and then a B, from C to B to A, so this purple one first, then this one, it's purple plus red is blue. Purple plus red is blue. Okay? So blue minus purple is red. And so the red one can be the difference in the two. This is pretty useful when you have problems. Here's a kind of problem you might see this in an application problem. You start at an airport here, and an airplane is going this way, and you figure out that it's gone a distance of 1,068 miles, and then this one is going 910 miles this way, and we know the angle is 55 degrees. Now you may not, this is the math way of doing the angle that you type in here. Instead they may have given you this bearing angle of 35 degrees, so you have to figure out that you're supposed to type in 55 degrees here. Or they might have given it as a heading, and then you figure that out. Then here's the angle. Here is 171 degrees for the purple one. Okay, and again, you might have seen that as a bearing north 81 degrees west, or you might have seen the blue one as north 35 degrees east. But either way you draw it, notice this time they're tail to tail. And so to find the angle between the two, you're finding this angle right here at angle C, which is, in this case, 116 degrees. And then you're just solving for the other side. Again, you have some options there. You can think of these, do these in components. And again, be the components of the blue component minus the purple components. We'll give you the components of the red. And turn around then and turn back to r and theta, and get whatever angle you need for this, whether it was a bearing or a heading or just a direction angle as we do in math. Or you can just use law of cosines to solve for the length of the missing side and the missing angle right here at B, and then somehow use that angle to come up with, say, this bearing angle or the math angle, which is the angle between here, and here. So this one doesn't have all the details worked out, but it does work out the final answers for you. Also, this one it is set up so that you could actually type in some pretty large numbers here for these links, and that's okay. And what you do is you can scale this back. So if I put, if I change that 7 to a 9, now it makes the whole thing bigger. If I change that to a 2, now the whole thing is quite a bit smaller. And so I can experiment with this number a little bit until I get the numbers I want in the blanks, and still get the drawing to fit on the page. And now I have a nice scale drawing worked out for a difference here. So for example, you got an airport. This plane goes 1,068 miles. This one takes off about the same time. Goes 910 miles this way at a math angle of 171 degrees. The way we measure the angles in math, this one's at 55 degrees. Then say, okay, what's the bearing and distance here? Or maybe the original one said it was a north 35 degrees east. This one went north 81 degrees west. What's the bearing and distance of plane A from plane B? Notice if you're saying that way, you're measuring from plane B. Plane B is the origin, so the bearing angle would be this pink angle here. For angle from B to A, it turns out to be 25.86 degrees northeast. So that's north 25.86 degrees east, and the distance turns out to be 1,679.53 miles, if this is miles. Anyway, so you get an idea kind of how that works. And again, you can also do it by resolving the components. You can see that this one is going east and then north component. This one has a west and north component. Add the two north components, and that we're subtracting. So subtract this one, and then have the subtract this one here. That means you're only going up as much as from this intersection up, which would be the component of the red one. The other way to do it, and then the left-right or east-west. This one's going east this much, but you go back west that much. Okay, but you're subtracting it, so you reverse this one. So you're going from this point of intersection here to the right to here, plus this. So that means you're going all the way from here to here to the east. So then you can get it in component form if you want to do it that way. So once again, just review. If you want to add vectors, you start here at an endpoint, go to the other to the end with the first vector, to the initial to terminal. Then the terminal point becomes the first vector becomes the initial point for the second vector. So this is composition of translations. And then the final point for the second vector is the final point for the sum. So the sum goes from initial to final. When you're subtracting, then you want to put them tail to tail, and the difference will be this red one with the arrow on one end. It'll be subtracting one direction, and the arrow on the other end, it will be subtracting the other direction.